Hey, good day, calculus students. I'm here today to continue on with our lessons on 11.1 on sequences and 11.2 on series. I'm going to go over those things right now, do some more examples from 11.1 that we didn't do, and then move forward and talk about 11.2. So here's the first problem. This is number 59 in the text, and the directions want us to graph this sequence and then decide whether the sequence is convergent or divergent. If it's convergent, guess the value of the limit, and then they want us to prove our guess. All right? So let's do that right now. So when I did this on my graphics calculator, I set my calculator to sequence mode. All right, so under the mode, type the function in, inverse tangent of n squared over n squared plus 4, and then I graphed it. And essentially you would get something that looks like this. At 1, you'd have a value, and then you'd have another value, and another value, and another value. And it kind of looks like this will level out according to whatever that line is. Now, it's very hard for me to tell if it's convergent or divergent because I can't really go way out here to infinity on my calculator and see if it's going to keep getting higher or if it's actually approaching some number value. All right. But I scrolled out on my calculator a little and I see it looks pretty flat. And so my guess is convergent, and that's what they wanted us to do from the graph. And then we could guess the value of the limit from the graph, and I could do that by just picking a value. All right. And that value is 0.7852 now, that I picked. All right. And so that's pretty close, but that's not a lot. So the real issue then becomes, can you prove the guess? Can you actually show that this is convergent? And the answer is yes, you can show it's convergent. And so really we want to take the limit as n goes to infinity of the inverse tangent of n squared over n squared plus 4. And now this is a function of a function, so we could say it's the inverse tangent of the limit as n goes to infinity of n squared over n squared plus 4. And so this is a rational function, and so we use our techniques for limits on that, which essentially is we multiply the numerator and denominator by 1 over n squared. So we're going to end up with the inverse tangent of the limit as n goes to infinity of 1 over 1 plus 4 over n squared. Okay? And once we see that, as n goes to infinity, this term will go to 0, and we're left with 1 over 1. So we see that we get the inverse tangent of 1, and that is equal to pi over 4. And if you take 3.14159, so if you take pi and divide it by 4, you're going to get 0.7853, which is really close to our guess. Actually, 0.7854. Okay? So this one is convergent, and it converges to pi over 4. So I would make sure to say converges to pi over 4. All right? And there you go. That's that problem, a graphing problem. So let's look at another problem. Okay, so here's our sequence. The directions say determine whether the sequence is increasing, decreasing, or not monotonic. Is the sequence bounded? Now, there are a couple of ways we could do this. Okay? Increasing, decreasing, or not monotonic, or monotonic, and decide that. So what we'd like to do is we'd like to decide if it's increasing or decreasing. Now, surprisingly, just think of this as a function. Let's look at f of x equals 1 minus x over 2 plus x. And you can take the first derivative, which is equal to 2 plus x times negative 1 minus 1 minus x times 1 over 2 plus x, quantity squared. It's quotient rule. And that's going to be negative x plus x in the numerator. So those disappear. So we'll have a 2 minus 1, or 1, over 2 plus x quantity squared. So that's the first derivative. And so we want to check for increasing and decreasing, right? And so the denominator is undefined at x equals negative 2. So x equals negative 2 is a critical point. So now we're doing first semester stuff here, right? So I mark negative 2, and I need to check the values of x less than negative 2, all right? Which would be like a negative 3, and so I can check it in the function here. And since it's squared, it's going to be positive, which means it'll be increasing, okay? And then I pick a number bigger than negative 2, say 0, and the first derivative will be positive, so therefore it'll be increasing. So we could then, based on this, we could then say, and because it's a sequence, the n values have to be essentially greater than or equal to 0. Integers greater than or equal to 0. So we're really looking at this half of the graph. But we know from this piece of information that the function is always increasing when the x values are bigger than negative 2, and certainly n greater than or equal to 0 is larger than negative 2. This is greater than negative 2, thus a sub n equals 1 minus n over 2 plus n is increasing. Now, that's one way I could show it's increasing, okay? Let's take another way, just in case the text did this. So what's the other way to show it's increasing? Well, if you look at a graph, and suppose you have x1 and x2. If the graph is increasing, then that if x2 is bigger than or equal to x1, then that means f of x2 is bigger than or equal to f of x1. That's also increasing, okay? In fact, this is the definition of increasing. So in other words, we need to pick an x1 less than or equal to an x2, in this case an n. So suppose we have n1 less than or equal to n2, okay? And then we want to look at a sub n1 and see if a sub n1 is less than or equal to a sub n2. Okay, that's what we have to do, like a little proof here. All right, so let's move that up. So a sub n1 is equal to 1 minus n1 over 2 plus n1. And a sub n2 is equal to 1 minus n2 over 2 plus n2. Okay? And now we need to look at those and see if they're going to be a sub n1 is less than a sub n2, or you could say a sub n2 minus a sub n1 is greater than or equal to 0. So you could show that if you subtract these and it's greater than 0, then you're good. And so I actually kind of like this approach. That's sort of increasing rather than comparing them. But you can do both. It doesn't matter. So what I'll do is I'll take 1 minus n2 over 2 plus n2 minus 1 minus n1 over 2 plus n1. And I have a question, how does that compare to 0? So I just continue to solve through that, all right? So it's just algebra. So I get 1 minus n2 times 2 plus n1 minus 1 minus n1 times 2 plus n2, and then and that's all over the common denominator, 2 plus n2 times 2 plus n1, which we can, if we're comparing it to 0, well, we can't really multiply, we got to keep it. Okay, so then the numerator then becomes 2 minus 2n2 plus n1 minus n1 n2. And then over here, we'll have 2 times 1, which is minus 2. And we'll have 2 times negative, so negative 2n1 with a negative is plus 2n1. All right. And then we'll have 2n2 times 1, or we'll have n2 times 1 with a negative, so that'll be minus n2. And then we'll have n2 times n1 with a negative and another negative, so that'll be plus n1, n2. And that's all over our least common denominator right now, okay? So now if we look at that, notice that we get a 2 minus a 2. Those disappear, all right? Those are gone. We get n1, n2, and a minus n1, n2. Those disappear. So what we get left with is we get a minus 2n2 plus n1 plus 2n1 minus n2. All right? All over the least common denominator. And if we manipulate this around to 2n1 plus n1 minus 2n2 minus n2 over the least common denominator, we end up with, factoring the n1, we get 2 plus 1 minus n2, doing grouping factoring, which will be negative 2 minus 1, like that. Oh, I factored a negative, so it'll be plus. Okay? So this will be equal to 3n1 minus 3n2, or 3 times n1 minus n2, like that. And you can look at all the factoring. And that's over our least common denominator, which, if you'll remember, was 2 plus n2, 2 plus n1. Okay. So now let's look at this. All right. Is this going to be greater than 0 or not? All right. If it's increasing, it should show us n2. Hopefully I didn't make a negative sign mistake, which could have happened. For increasing. So for increasing, if you'll notice, these have no effect. These are just positive, because n1 and n2 are both greater than 0. But the way we started out with this, we said n2 was bigger than n1. So if n2 is bigger than n1, then this is a negative number, whereas these are both positive. That means this whole thing is less than 0. And in order to show that it was increasing, we needed to show that a sub n2 minus a sub n1 was greater than 0. Oh, so this says it's decreasing. Oh boy. So that's opposite. This tells me I might have made a negative sign mistake, because I should have got an n2 minus n1. But somehow I have a negative for the n2s. Negative n2, and you get... Okay, well, there you go. There's my mentality. So now, one way, using calculus, we showed it was increasing. All right. Because the function is increasing, therefore a sequence picking specific values one after the other is going to be increasing. And all of a sudden, I've now shown it's decreasing using algebra. And so, that means I'm going to go back and check all my work, which really sucks. But I'm not going to do it now. So, but I wanted to show you those two approaches. I actually like the calculus function approach to just decide, are those values increasing? And it makes it really easy to check it. It's much more difficult with algebra because you can do what I probably did, which is make a negative sign mistake. Okay? So we're going to leave that as it is, that this is an increasing function, despite my error, which says it's a decreasing function. Okay. And so I am not sure what I did. A sub n2 minus a sub n1. The bigger one minus the smaller one, if it was increasing. Okay. I'll just think about what I did. I think my signs are right, but I may have made a mistake. So I'm a little confused here, but that's okay. That happens on problems, and so you have to think through what the issue is. In any case, what I have done is I have decided I have an increasing function. and it's always increasing. Therefore, it is monotonic. Okay? That's what monotonic means. Now, what's our theorem say? The question is, can we bound this sequence? Okay? Can we bound it? And to bound the sequence, that means we just need to find a number. If it's increasing, that means we need to find a number that's always above this sequence. Okay? We just need to find a number that's always greater than the original sequence, which is 1 minus n over 2 plus n. Okay? Sometimes a graph can help us pick that number. All right? So I'm going to graph it real quick and look. And ta-da, I found my mistake. The mistake was not with the algebra. Turns out I did the algebra correct. The mistake was with the calculus. Right here, -1 times 2 is -2. Minus 1, that makes the numerator -3. And since that's always negative, because the denominator is always positive, that means this is decreasing. Now, another easy way sometimes is to graph, and the sequence of this would look like this. So it's decreasing from left to right as you look at the graph. And so it's always decreasing. So it turns out all this algebra was correct. Okay? So it is negative. And so it is decreasing. So it's decreasing. That's monotonic still, because it's always decreasing. Okay, so now the issue is, what is it bounded by? Okay, and this is where I said the graph could help us. So if we look at the graph, and we really just need to look at the positive portion of the graph is doing this, and it looks like it's going down towards some number. And so we just need to pick a boundary and then see if it satisfies the equation, because whatever we bound it by, we want it to satisfy the equation. Okay? And so I'm thinking -2 is going to be good enough. Okay? And so I want to show that 1 minus n over 2 plus n is greater than or equal to -2. Okay? And so that's 1 minus n is greater than or equal to -4 minus 2n, which is n is greater than or equal to -3. Now, remember what we said. N, in our case, is always greater than or equal to 0. That's the assumption. So since we get n is greater than or equal to -3, we know that this function is not only always decreasing, but it's bounded by this number. It's bounded by -2. Therefore, we have a monotonic bounded sequence. Therefore, I know this is convergent. I know the sequence is convergent. Now, I want you to think about that. What was our process? Okay, the first thing we had to do is we had to figure out if it was increasing or decreasing. I showed you two ways to do that. One is to use calculus, just don't make mistakes. And the next one is the algebraic approach. And you want to, and you could do that by taking the second one minus the first one and then simplifying it to a point where you can tell if it's negative or positive. And then you'll know if it's greater or less than 0. In our case, it was less than 0, which means always decreasing, which agrees with the calculus we used earlier. Okay? At that point, then this looks a little sloppy. I looked at the graph and I wanted to pick a bound, a number that it would bound it. And I picked -2. Now, I maybe could have picked -1 because it looks like it approaches -1. Why do I think -1? Because if you remember from pre-calculus, (n over n) in the numerator and denominator, that gives you a horizontal asymptote. Remember the ratio of those? At -1. And horizontal asymptotes are what we're looking for here. They're the bounds of the sequence. Okay? But you can, it just has to be bounded. It doesn't say you have to bound it by the exact value of the sequence. You just need to bound it. So that's monotonic, and I wanted to make sure we did a little, one of those problems so you could think about it. Okay? All right, I am done with this part of the video. Let's move on to 11.2. Okay, so we're going to talk about series now. So the first thing I want to talk about series is just the general comparison to a sequence. If we have a sequence, a sub n equals like 1, 1/2, 1/3, 1/4, etc. Okay? And that sequence continues forever. Then the series, so this will be, this a sub n, this will be the sum of the a sub n's, okay, using the Greek letter sigma, is going to equal 1 plus 1/2 plus 1/3 plus 1/4, etc. Okay? Now, when we say convergent for a sequence, we mean that this sequence is approaching a number. All right? In this case, we can see that this one will be convergent and will approach 0. Okay? And so 0 is the limit as n goes to infinity. You know, that's sort of, what would the last term be if you could get to it? Right? And that's convergent. Divergent would mean they don't approach any specific number. Okay? When you talk about convergent with a series, what you are saying is that it has a finite sum. And just because a sequence converges doesn't mean that a series will converge. Okay? And so you want to be careful not to mix those up. And so actually for this sequence, this is called the harmonic series, and it is divergent actually. It's actually the, what would you say? The smallest divergent series. It's actually, there's some really clever stuff you can do that are beyond the scope of this class. But anyway, hopefully that helps. Now let's look at a little notation for series. You see the Greek letter sigma, that means sum. So when we're adding the terms of a sequence, we'll say the sum of the a sub n's, where a sub n is a sequence that has some formula. Okay, so for instance, if a sub n was equal to 1 over n, like it is in the harmonic series, then this would become the sum of the 1 over n's. Okay, we could substitute the formula there. Now, the other thing we do is we usually tell it where n is going to start and where it ends. And so for our course, we are really concerned with infinite series, but you will encounter some finite series where you might want to just add up the first 10 terms of the sequence. Okay? But this is the notation. This is what it means. Okay? All right. So let's move on. Okay. Oh, okay. I'm sorry. I should have paused the video. The next thing they actually talk about is partial sums. So it turns out if you have a finite series, okay? So say we have the sum of this particular series, okay? So it's really like the sum of the n's from n equals 1 to 4, okay? So when n is 1, you get 1, and then when n is 2, you'll add 2, and when n is 3, you add 3, and when n is 4, you add 4. Now notice this partial sum exists, all right? In fact, you end up getting 10, all right? And that's really 1, 2, 3, 4, like that, all right? That's really 1, 2, at the sum 1, 2, 3, 4 can be written as this particular series. And we have a partial sum. So it turns out all sequences have partial sums. And your partial sums could be quite large, right? From 1 to 1,000 of the first n numbers, right? And that's going to be a large number, okay? And so we want to be able to deal with partial sums, but then we want to be able to deal with infinite sums, because we want to find out which series are going to converge. Now, the series n, a sub n equal to n, this is not going to converge, all right? Because you just keep adding numbers to it, it gets bigger and bigger. So it's not going to be a very nice series, okay? So your textbook gives you a definition of a series, all right? And the definition of what convergent is, okay? All right, let's go on. Okay, I want to talk about some notation a little bit, and kind of get you used to this, and then you'll have to work through it and develop your own sense of how it's working and so forth. But what we want to do is we want to define the partial sums. So this is called the nth partial sum. Now remember, partial sum is you only add up to n terms, okay? And so the sum of a sequence a sub I from I equals 1 to n is equal to the nth partial sum. And we write that as s sub n. Now, if this happens to be a formula or something like that, if you take the limit as n goes to infinity of the partial sums, i.e. the sequence of partial sums, If that is equal to a number, then that is convergent. Then that's what we mean by convergent for a series. Okay? So a lot of our goal where we're going to have the sum of this sequence, and what we'd like to do is be able to find a formula for the partial sums. If we have a formula for that, then we can check the limit of the partial sum sequence and see if it's actually equal to a number. If it is, then the series is going to be considered convergent. Okay? So these are sort of the layers, and this is definition 2 in your textbook, and you definitely want to look at that. All right? So they actually go through an example in the text. I would say example 1 you definitely want to look at. We'll do a problem like that. But look at example 1 and then also example 2. So you may remember that you studied arithmetic and geometric series. And the geometric series is a very important one. And that's where you have a first number in your sequence, and then every succeeding number in the sequence is multiplied by the same number over and over. So you take your first number and you multiply it by a number, and then you take your first number and multiply it by that number squared, because you're multiplying by the number again. So each succeeding term, it comes from the term previous. You could define it recursively if you want. And this is a geometric series, and this is a formula for a geometric series. The sum from n equals 1 to infinity of a times r to the n minus 1. Okay? Now, when you have that, one of the things you want to do is you want to write out, what do the partial sums look like? Okay, what would a partial sum look like? So let's do that. Here's a partial sum. A plus AR plus AR squared. Sorry, let me do this a little different. Let me do it how I would teach a pre-calculus student how to do this. So let's do a partial sum. S sub 1 would just be the sum of the first term. That would be A. S sub 2, the next partial sum, would be the sum of the first two terms. So that's A plus AR. Okay? S sub 3 is equal to A plus AR plus AR squared. S sub 4 is equal to A plus AR plus AR squared plus AR cubed. Okay? And then what we want to do is we want to make a guess at what S sub n looks like. Well, that's going to be these right here for sure. But what we want to do is we want to look at what happened here at the end. And so let me kind of highlight the ends here. And I'm going to put R to the 0 right there. Okay, so let's look at it. In our partial sum, compare the index to the exponent. So the index is which partial sum we're talking about. The exponent is actually the last exponent that shows up. And what you notice is that exponent is always one less than the index. That's why when you write out this nth partial sum, it's a times r to the n minus 1 for the last term that you add. So this would be the general form for any partial sum. You just need to tell me n, and then I could write it out, no matter how big or little n is. Okay? So once we figure that out, now we're going to play a game. Can we find the sum? Can we find this actual sum? So what we do is we use a little trick. We say, let's take the partial sum and then let's add some multiple of that partial sum. Well, what would we want to multiply by it? The trick is multiply by the thing you've been multiplying all along, which is r. Now, let's look at this. This one becomes a plus ar plus ar squared plus dot 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 ar to the n minus 1. But if you multiply all these terms by r, you end up with ar plus ar squared plus ar cubed plus ar at the end. Ar to the n, excuse me. Now let's look at that. And what we want to do is we want to find an explicit, this is a recursive kind of formula. We want to find an explicit representation of what that sum is. And so what we do is we see this little trick and we go, wait a second. These are the same. These are the same. All the way down to the end. And so what we do, we just look at S sub n and r times S sub n, which I've done here. This one's S sub n. This is r S sub n. And then we decide what we're going to do with it. And what we're going to do with it is we're going to subtract, not add. I apologize. And when we subtract it, if we take this one and subtract the one above it, then everything at the end disappears except for the a. So we'll get a. In the same way, if we take the second one and subtract the first one, we are left with the ar sub n. So what we get is plus ar sub n. Okay? And then we can do a little factoring. S sub n times r minus 1 equals a times 1 plus r sub n. And we can solve for S sub n. A times 1 plus r to the n over r minus 1. And this is the sum of an infinite, or a partial sum of a geometric series, given that you know what the last term, how many terms you want in that sum. Okay? And so we can then apply this as a formula. Okay? Which is what we do in pre-calculus. For instance, if you have the geometric series, let's say 1 plus 2 plus 4 plus 8 plus 16. So you multiply by 2 every time. So the common ratio is 2. All right. And say we want to know the sum of the first 100 terms. Then it would equal, the first term is a, so a is equal to 1. It would equal 1 times 1 plus 2 to the 100th power divided by r minus 1. Which would be 2 minus 1. All right. And I'm looking at this right now and I'm asking myself, what the heck did I do? Oh, sorry, that should be a -1 there. I apologize. That should be a -1. So now it's correct. Okay. So yeah, sorry, that should be a negative a right there because I'm subtracting this, so the a gets subtracted. Okay? So r sub n minus 1 over r minus 1. And now we fill in the formula, and so this would be negative 1 plus 2 to the 100th power over 1. So this would be what it adds up to. Okay? And that's the typical situation for a geometric series. So I want you to look through that. They then show you that for every geometric series, if r is between 1 and negative 1, then you can actually find the limit of partial sums. If S sub n is equal to this formula, you can actually find the limit of partial sums for that formula. And it will equal a over 1 minus r. And you might remember these formulas from pre-calculus if you did that. And this is summarized in a theorem or they summarize the results in a table. And so if r is between 1 and negative 1, it's convergent, and you can find the sum. And if r is greater than 1 or negative 1, it will be divergent. And so they then use this to do a number of examples, okay? And so we want to do that. They also, let's see, they do some other geometric series. Let's see, they do some other examples. So we'll do some examples that'll kind of highlight these, and we'll go from there. Okay? Okay. They then give us a test for divergence too. So the geometric series is kind of the key for this. Okay, so here's a problem. They'd like us to find some partial sums, all right? And so what we'd like to do is I always like to list out some terms. So if n equals 1, okay, I get 7 squared, which is 49 over 10. So that's the first term, okay? First term, all right? Now, when n equals 2, okay, so there's one partial sum. So this is S sub 1 is equal to 49 tenths. So what's S sub 2? Well, it's going to be 49 tenths plus what? Well, if n is 2, then my sequence, which is right here, my sequence becomes 7 cubed over 10 squared. So 343 over 100. So that's S sub 2. What about S sub 3? Well, now it's 7 to the 4th power. So I'm going to rewrite this a little bit differently. I'm going to write it as 7 squared over 10 to the 1st plus 7 cubed over 10 squared plus 7 to the 4th over 10 cubed. And this is the next term, all right? And so I can do that ad nauseum to write partial sums. So there's an example of writing partial sums for a given sequence, okay? Now, we want to then decide, is this series going to be convergent or divergent? Okay? Now, what I notice is I have this 7 and 10, and they're both raised to a power. Now, if they were both raised to n, it'd be 7 tenths to the n power. right? And so maybe there's a way I could rewrite that sequence to help me. So what I do is I think, okay, what if I write it as 7 to the n times 7 to the 1 over 10 to the n? Oh, that's going to be equal to 7 times 7/10 to the nth power. So this is probably a better way to write it. So sometimes you want to see if you can rewrite your sequence. So now let's look at this sequence. So we have the sum from n equals 1 to infinity, and we're going to multiply whatever terms we get by 7, so we can pull the 7 out front. And then really we have 7/10 to the nth power. Now, this is a geometric series, okay, with r equals 7/10, which is less than or equal to 1. Therefore, this series converges. Okay, guys, I apologize for that phone interruption. Okay, so therefore I know this series converges based on the geometric series stuff. Now, since we already know what a geometric series converges to, and I asked you to look at that, the rest of that on the bottom of page, on the bottom of page, I lost the page, there it is, 749, and the top is 750. You want to look through that, and that'll give you what this sum is. But the sum then is going to be a over 1 minus r. So we know that essentially we want to take the limit as n goes to infinity of 7/10 to the n. That's what we want to do. We want to take the limit of partial sums. And that is going to equal the first term. So when n is 1, this is 7/10 over 1 minus the common ratio, which is 7/10. All right. And then we simplify that. So this is the a over 1 minus r. And so that gives us 7/10 over, what is it? 3/10? So this sums to 7/3, but that's not quite right for this problem. We've got this whole 7 multiplied by it. So our final sum is 7 times 7/3. And so it converges to 49/3. All right? And that's it. That's all you have to do if you encounter a geometric series. But you have to think about how you might rewrite sequences that are part of the series and so forth. So that's an important thing to think about. Let's go on. So this one converges because it's a geometric series. So let's go on and do some others. So here I have this, and I want to write this in some way so that the exponents are the same. So this is going to take me a little work, but this is where your algebra helps you. E to the 2n is e to the n plus n, which is e to the n times e to the n over 6 to the n minus 1. And so this basically means, oh, I can pull one of each of these e's out in front, like we did this 7, so I can have e times e, or e squared, times the sum, n equals 1, and then we'll have e to the n minus 1, e to the n minus 1, over 6 to the n minus 1, okay? And so now, that means we can write this as e times e over 6 to the n minus 1. Like that. Because they all have the same exponent, right? So, what is e times e? Well, it's bigger than 6. You can check it. E squared is bigger than 6. Since it is, e squared over 6 is greater than 1. Therefore, this is a divergent geometric series. Okay? I could say something like, wow, that rain's loud.
I wanted to make a guest appearance.
Huh?
I was hoping to make a guest appearance on your film.
Yeah, somebody made a guest appearance. I'm going on. Okay, so anyway, based on what I see, I think that's enough for this video to get through the geometric series, and then we'll look at some other series in the next video and do 11.2, finish it up, and do some of 11.3, I believe, looking ahead here. I think that's enough. Yeah, we'll do. There'll be some other tests we want to look at. Okay, we'll talk to you later. Good luck. Bye. Not quite bye. You won't be able to do all the problems, but kind of focus on the geometric series ones and make sure you can get through that. If you have any questions, be sure and email them. Okay, now bye.